Alright guys, welcome to this set of videos, and what we're going to do is continue with this theme of looking at algebra that we can do with polynomial functions. And specifically here in this chapter, we're going to take an even further look at roots and zeros, right? Roots or zeros being x-intercepts. Where does the polynomial cross the x-axis? Couple of objectives or learning targets for you, things that you should be able to do by the time we get to the end of this set of videos and this section of notes are these things right here. First, determine the number and types of roots for a polynomial equation, and then finally, find the zeros of a polynomial function. Very, very similar objectives to ones that we've already seen in previous sections. We're just going to sort of continue that same idea of being able to find solutions, the roots, the zeros, the x-intercepts, right, of a polynomial. Where does it cross the x-axis? Okay, so what we're going to do here is just as a little bit of review as we kind of jump into this section, I'd like you to use the factoring methods that we've already looked at back in section 5 and section 6 of this chapter. We're going to go ahead and factor the following polynomials I've got for you. So let's get warmed up here as we jump into this section with a couple of factoring problems. So I want you to find the zeros for this first polynomial I've got here. Recognize that it's already set equal to 0. That is sort of like your dead giveaway, right? When you see a function set equal to 0, you should immediately think they want me to find the zeros. Where does it cross the x-axis? Now that's going to require us to do some factoring. So we looked at 7 methods for factoring in section 5. A number of them were actually a review from chapter 4, where we learned factoring methods for quadratics, but several methods in section 5 of this chapter. And then just in section 6 we found the factor theorem, where we're able to take a factor of a polynomial, determine if it actually is a factor by doing synthetic division, and then sort of factoring from there the reduced polynomial. So we'll get to all that here in a second, but we're starting with this one. And since I have a trinomial and I recognize that 9 is a perfect square, I wonder if this is maybe a perfect square trinomial. So let's find out. I could rewrite this as an x squared, and I could rewrite this guy, the 9, as a 3 squared. The middle is going to have to be 2 times a times b. So plus 2 times a, which for me is an x, times b, which for me is a 3. I apologize, I'm squeezing a little bit there. But anyway, this is the formula, right? This is the general formula for a perfect square trinomial. So does my middle come out to be 6x? Yes, it does. 2 times 3 is 6x. So this fits the general formula for a perfect square trinomial, which means I know that my two binomials, it'll factor into a plus b times a plus b. Well, my a is an x, my b is a 3. I write it twice. And again, we prefer to write that as a binomial squared. Now, it was set equal to 0, which means, right, I'd set this whole thing equal to 0. X plus 3 squared is equal to 0. Take the square root of both sides. X plus 3 is equal to 0, which means x is equal to minus 3. And that just happens to be the answer that you would get twice, right? I have 2 of them, so this guy would have a multiplicity of 2. We talked about that a few sections ago when you get a double answer, right? When the graph, the polynomial, comes down and touches the x-axis but doesn't cross the x-axis. We call it a point of tangency. That's exactly what we've got at x equals negative 3. My polynomial will either come down and touch the x-axis or come up and touch the x-axis, but it won't cross. This counts as a double 0. It shows up twice, and we said that that was multiplicity. Here's another one for you. X cubed plus 25x equals 0. Let's go ahead, and it looks like I have a GCF, so we'll factor out that GCF. That's going to leave me with an x squared plus 25. That's all equal to 0. Well, the zero product property lets me split those guys up. X equals 0, and x squared plus 25 is equal to 0. Subtract the 25 to the other side. And right away, I can recognize in order to get this x by itself, I'll have to take the square root of both sides. I'm going to be taking the square root of a negative number, which means I'm going to get imaginary solutions, which is perfectly okay. It's going to happen. So I take the square root of both sides, and I wind up with x is equal to plus or minus the square root of minus 25, which we know is going to come out to be plus or minus 5i, right? Because the square root of 25 is 5, and I pull out the square root of negative 1, which becomes my I. And so I have 3 zeros. I have x equals 0 is a real 0. I have plus 5i and minus 5i are my other 2 zeros. They just happen to be imaginary. All right, and I got another one for you here. These first two were factoring methods we learned in section 5 of this chapter. This one right here is going to be a review from the last section we just did, section 6, where I've given you a polynomial. I've told you that x plus 1 is a factor. So we're going to go ahead and do the synthetic division, get our reduced polynomial, and work from there. Remember the way this works. You take your factor, x plus 1, set it equal to 0 and solve, which means x is equal to minus 1, and then we set up our synthetic division. Make sure I don't need any placeholders. 3, 2, 1, 0. Everybody's there, so we're all set. Negative 1 goes inside the box. 1, 4, minus 7, negative 10. Bring down that first term, or bring down that first constant, and then it's multiply, add till you run out of numbers. Negative 1 times 1 is a negative 1. That's going to leave with a positive 3. That's going to be a minus 3, which of course is a negative 10. It's going to leave with a positive 10. So I get a remainder of 0, which I knew, all right, I told you x plus 1 was a factor. I already told you that. So you knew you needed to come out with a remainder of 0. If you didn't, something would have gone terribly wrong. So now I can rewrite the polynomial I was originally given as my factor, x plus 1, and my reduced polynomial. Well, my original degree was third degree, so that means that this needs to be 1 less than that. Second degree, x squared plus 3x minus 10. Again, that's all equal to 0. I'm just rewriting, right? If you were to multiply this guy together, right, distributive property, to multiply this out, you get right back to the polynomial you were originally given. So all I've done is taken this polynomial that you were given and I've rewritten it as these two factors, right? This and this polynomial are the exact same thing. They're mathematically equivalent. So because this was equal to 0, this is now equal to 0 as well. And then we're going to go ahead and factor this guy, or at least check and see if I can. So let's see how this goes. Let's see, 10 and 3, absolutely, this is going to factor into two binomials. The easy bit, x and x, x times x gets me x squared. Slightly trickier bit, I need two numbers that multiply to a negative 10 and sum to a positive 3. And I believe that a positive 5 and a minus 2 is going to do it. Minus 2 plus 5. That's all equal to 0. Negative 2 times a positive 5 is a minus 10. And then a negative 2 plus a positive 5 gets you that positive 3. Zero product property to split them all up and set them each equal to 0. Oh, hold up. Sorry, apologize. I forgot my minus sign there. Should be a negative 5. And there we go. I've got 1, 2, 3 zeros for this polynomial, and that makes perfect sense since the degree of the polynomial is a third degree polynomial and the fundamental theorem of algebra tells me I should get 3 zeros. Here they are. X equals negative 1, x equals 2, and x equals negative 5. That's where this polynomial will cross the x-axis. All right, having just mentioned the fundamental theorem of algebra, here it is one more time for you guys. I've got it all written out as its definition. The fundamental theorem of algebra, I apologize, hold up, let me slide up. There it is right there. So the fundamental theorem of algebra, just again mentioning it here, and then the corollary, which is really what we're using, and that corollary states that the degree of a polynomial is exactly equal to the number of zeros that polynomial will have. So if you know the degree of the polynomial, you know how many zeros that polynomial will need to have. So we've already taken a look at all of that, and again, let me highlight it for you because really when it comes to the fundamental theorem of algebra, we're technically using the corollary of the fundamental theorem of algebra. This is what the fundamental theorem of algebra actually says. This is just kind of a result of that fundamental theorem. We refer to it as a corollary. But anyway, same thing. So let's just, again, real quick, since we were talking about it, review a couple of things you can then do with the fundamental theorem of algebra. So here's what I've got for you. I've got a number of different polynomials, and what I ask you to do is use the fundamental theorem of algebra to determine how many zeros each of the following polynomials will have. So take a look at the first one, and I recognize right away that's a third degree, second degree, 0 degree. Third degree wins, so this is a third degree polynomial, which means I will have 3 zeros. One more, fourth degree, third degree, first degree, 0 degree, fourth degree wins. So this is a fourth degree polynomial, and that means that I will have 4 zeros. And the last one, fifth degree, second degree, 0 degree, fifth degree wins. This is a fifth degree polynomial, and that means that I will have 5 zeros. So if you were to take the time to factor each of these polynomials, work them out to find their x-intercepts, you would get 3 zeros for this one, 4 zeros for this one, 5 zeros for this one, and again, it's just a great way to check your work. If you didn't wind up with 3 zeros, you know you made a mistake and you have to go back and figure out what you did wrong. All right, guys, head on over to the next page of the notes and we'll take a look at a few other things dealing with zeros and x-intercepts for polynomial functions, so I'll meet you on the next page.